As introduced, my name is Adam Katz. I'm one of the lead character effects artists at Animal Logic, and I'm going to be covering how we automate character effects today. We use this method throughout Peter Rabbit, and we're also using it on some current and future projects. So first things first, just a bit about who Animal Logic is. We were founded in 1991. We've got creative studios in Sydney and Vancouver, and development offices in LA and Sydney. We work predominantly in commercials first, while then moving on to VFX features. We did The Matrix and Happy Feet, which was the first animated feature to be done in Australia, and it won an Oscar. And more recently, we did the Lego Movie franchise and Peter Rabbit. And Peter Rabbit kind of brings us back to the automated character effects pipeline. So the first thing is I want to start by showing you some examples of what our setups can do. And the main thing to remember as you're watching this is that essentially it's 100% automated after animators have checked in keyframes of what they want to see. So let's start with a clip.
We all ready?
Yep, absolutely, always.
I guess. Love you guys. Now let's do this.
Show me your teeth. You like a goat, like. It was you! I knew it! Hello. His face was so classic. He was like. Do you know what? That would never have worked.
All right, so that was Peter Rabbit. So for today's speech, I'm not going to use Peter Rabbit, we're going to use a test character. So let me introduce you to that test character. So this is the character that we use while testing that everything's working. And you can see it running around and having a pretty good time. Now, the setup for this character in general would be created before the character effects team starts working on a shot, which means all the lighting, the shading, the rendering settings, that's all set up and ready to go for us. And what we're going to look at is the automatic process we have to create the character effects for this and any other character, and that includes working on the geometry of the body, the clothing, and the fur. So as an overview, we want to look at how we build our pipeline for automation while also accommodating specific shot works that artists can use on the characters. So we automate all aspects of this within Houdini. And when those processes complete, they move on to the rest of Animal Logic's pipeline, which picks things up, lights it, renders it, and so we can get feedback for our work. So specifically in the talk, I want to look at how we set up our pipeline for automation. That includes geometry preparation, de-intersection, cloth simulation, hair simulation, importing and exporting of data. We're going to look at some of the technical details about it, some of the challenges we found with it, and consequences from using this type of setup. And I'd like to give a big shout out to Roger Franson. He really helped create the initial Houdini setup on Peter Rabbit 1 that this was all worked on, amongst other people as well. So the purpose of what we want to do is to create engaging photorealistic characters within a live action world. And that means we want high quality dynamic cloth and fur that can be used in a range of different shots. So that might be slow emotional performances, frantic action scenes. The characters are going to be interacting with each other and also with live action actors and actresses. And there's going to be a range of different weather conditions. So like wind and rain, things like that. So the first thing to know is that Houdini is essential to our process. The entire chart effects pipeline is contained within Houdini end to end. And what that means is we are importing USD data from the animation department. We're taking that data into Houdini and processing it. We're importing it into SOPs. We're splitting into different geometry streams like the cloth and the fur, etc. All the simulations completed within Houdini. And then at the end of that, we export that data as USD overs and defines. And what it means is that the artists never need to leave Houdini. They can stay within that one context of working. And we found that that amount of automation is really only possible with that procedural nature, combined with the amount of Python we can write and some fairly sophisticated ROP nets that we're going to look at a little bit later. Now, what are some challenges we found with this? Well, first, we haven't come across many studios that are end-to-end char effects within Houdini. Some will have parts in Houdini, some in Maya or other software. And that means that when we're looking to hire people, it's hard to find people that have done everything within it. Some will have some experience within it, but not for the full pipeline. For instance, they may have only done simulation or maybe post-processing or some data wrangling, but not everything. So really the question that we'll start with is, why is it that we wanted to automate character effects? Well, first, there's a pretty long history of automation in animal logic. Automatic renders were started on Guardians of Gahul in 2010. And in subsequent projects, we've automated character rigging, building, lighting, and compositing. Now, obviously not everything within those departments is automated, but we have a very well-connected pipeline, especially to get data between different departments. So when Peter Rabbit came around, our goal was to have a really efficient way to get shots to as close as final as possible. And with the director, he was very used to live action work and having rushes, and we wanted a way to be able to replicate that with our animated characters as much as we could. So with all those other processes already automated, we wanted to expand into character effects. We also wanted very quick and dynamic feedback as soon as possible to aid in animation reviews for both the animation department and for the director. And essentially showing just basic point informations or FERD informations wouldn't cut it. So the rough overview of what we do is we get an update from the animation department. That goes in and gets processed by Houdini, and we get a rendered shot at the end of that. We want to be able to process very efficiently. And basically, the amount of animation updates we get per shot and per character would just overwhelm our relatively small char effects team. So we had this process to be able to let us actually get everything done. We'd also like our artists to be able to concentrate on hero work. And so that means that if we have a shot, that might be split up into some hero work, which is going to come to the char effects team, and then a lot of other work, which is in a process called anim effects, which I'll get to in a second, and that's going to completely bypass our team. And all of that is going to come together for a final render. We also have the advantage of having a very large scalable farm with a lot of resources, which means we're able to push a lot of processing onto that farm concurrently with each other. There's also a pipeline that's driven by triggers, which basically means as soon as certain processes finish in the pipeline, it triggers the next ones to start and so on. And that can handle a lot of the steps without needing user interaction. And that goes throughout the entire process from assets all the way to final render. Okay, so all of this comes together within our automation process. So we basically have two different related pipelines around the process. And the first is called anim effects. And anim effects just means that it's the animation department's character effects. Then we also have something we call char effects. And that's the character effects department itself and what we actually do. So both of these systems are used to create shots, and they consist of the exact same Houdini setup. Anim effects runs automatically whenever the animation department checks in keyframes, whereas char effects is manually run whenever shot-specific changes are needed. So things like a simulation that needs to be art directed, or maybe a complicated collision in a shot, or possibly simulation errors like jitters or pops that might come. So the anim effects process consists of the following. So an animator is going to check in keyframes. That's going to then create a HIP file, which gets passed to Houdini, and that processes the geometry of the body. It simulates the cloth, it simulates the fur, and then it exports USD for the body, cloth, and the fur. That triggers the final render, which of course gets approved on the first try, and we all go home. That's anim effects. Now, char effects is very closely related. It's essentially the same, but when we had hero work or we had some simulation errors, The animation was updated, it would make a HIP file. Then a char effects artist opens up that HIP file and makes any changes that are needed onto the body or cloth or fur sections. They then send that file off to the farm, gets rendered like normal. Once those changes are approved, we have one more step. We take all of those changes and feed them back into the animation department. So when animation runs again, they'll pick this updated setup that has been set up specifically for that shot. So as they continually update the animation, we'll have all these shot-specific changes ready for them. The processing of all of that is inserted into a chain of jobs. And that chain of jobs triggers on new character updates from animation, which might happen, multiple times per shot because of multiple characters in that shot. And all of these characters run concurrently. And at the end of all that, they trigger a final render. So that's kind of the general process. Now, how we actually automate when we have a few troubling things, basically. First, the input geometry we get is not always finalized, and it may/will change point count. We have multiple characters that are automated with different needs. Some may have cloth, some may not, some may have fur, some may not. The animation is going to be updated frequently. We might get geometry that's intersecting. And basically, there's just way too many shots and characters to finish with brute force. So we do all of this within something we call a character effects rig. Now, it's not like a rig you'd have in Maya for animating something. It's just the term we use for our setup within Houdini. So I want to look at a high overview of what this Houdini process does. So basically, we first get the input from animation. That's a cached USD file. And that USD file includes body geometry, cloth, and fur. That data we do geometry processing on. We de-intersect it. We do a few other things. That leads into the cloth simulation, which leads into the fur simulation. And then that gets packaged all up and re-exported as USD. So to break this down into roughly the steps that we work with, we get our input USD. And the first two parts of that we use are something we call an animated skin mesh and a hair volume. Now, the animated skin mesh, this is just the basic part of the body that the fur is eventually going to attach to. The volume input roughly estimates about 60 to 70% of the length of the fur once it's attached to the smaller skin geo. And this geometry is what the cloth is going to collide against. So if we zoom in here for just a little bit of a close-up, this is the skin geo. That's the volume geo. And you can see these overlaid on top of each other. Now, when we put the fur in, you can see that the fur essentially just sticks a little bit out of that volume geo. And we actually run our cloth simulation first, and only after it's finished do we run the fur simulation. So we found that bidirectional simulation between the cloth and the fur was a little unstable and it was a lot slower. So we faked the pressure of the fur colliding with the cloth by colliding against this volume geo. We're going to come back to the fur in a little more detail later. For now, we work on our volume input. And we basically needed to ensure that our geometric inputs were good and valid. And it was the cause of two major concerns. So the first thing, and the most importantly, is that good inputs are going to equal good outputs. And what I mean is that if the geometry you're getting self-intersects or it collapses or it moves suddenly like in a frame, or it fails to leave gaps for the hair or cloth, like if the arm goes down to the body, then nearly all solvers are going to fail or they're going to get bad results. Also, the animation itself could end up with flipping joints or intersecting limbs or anything like that, especially when animators are working to camera angles or if they're used to working to camera angles. Now, since all of our inputs come from the animation department, I really couldn't stress enough how important their relationship is in the process. We made sure to talk with them extensively to make sure they'd have a really good understanding of what a good bind pose is, what good pre-roll is, and how self-intersections are going to cause issues in their renders, especially because it's automated on their side as well. So when they check something in, they want to see a valid render come back. Now, even with all those issues improved, we basically still have a problem. The volume mesh itself was often self-intersecting in areas of high flexibility, like the elbows or knees or thighs. And it was basically an unavoidable situation because the volume geo is only estimating where the hair would be, and the hair would be collapsible. The volume geo is going to intersect. So for instance, we might have something like this where the 2 feet come together. And so what we did to fix this was we took the mesh, we projected it onto an SDF or assigned distance field of itself, and that helped find intersection areas. Then we take that along with some smoothing and relaxing operations in areas of crossover, which leaves space for the cloth to move. So for example, this is that raw input, and then after we de-intersect it, we get something like that. And here's roughly them overlaid on top of each other. Now, a little more extreme example would be something where the leg of a character might be intersecting the hip a lot, and when we de-intersect, we get something like that, which was a lot better for simulating cloth width. The method we had, it wasn't that fast, but it was able to de-intersect intensely deformed sections. And since all of that could be chunked essentially, it wasn't a sim, it just depended on each frame, it went really fast. Now, I should say that we did test out using the Vellum detangle node within a solver for de-intersecting, and it kind of worked all right, but we didn't want to have to rely on a solver that could only run on CPU in sequence. We wanted to be able to split that up because we had the advantages of a render farm. So from there, we go ahead and we remove body parts that aren't going to be interested in the simulation, so like toes and fingers, things like that. And that's essentially the end of the body processing. So from there, we went onto the cloth. And for the cloth, we get a couple things. The cloth itself was built in Marvelous Designer, and we received 2 things. The cloth conformed to the body, like this, and we also get a flat input, as if all the panels were actually cut out of fabric. This input gives us reference for how long all the edges would be if it was laid out, and also the relative angles that the cloth should try to relax to. We also receive a thicker modeled renderable geometry, which is the thing that's actually going to be rendered at the end. So after we have that cloth, the first step we did was to remesh it to make it a lot better for simulation. So we basically take the very nicely modeled assets from the modeling department, and we remeshed into triangles that will let us simulate creases at arbitrary directions. Now, the nice thing about our remesher is we get the same point in primitive count, both for the flat panels and for the conform panels. And we did that by taking the position attribute of the conform panels, storing it as an attribute on the flat panels, remeshing the flat, and then reinterpolating those attributes back to the conform panels. And it let us have one-to-one correspondence in points. Once we have that, we move on to the cloth simulation itself. And we've done this in vellum or carbon, depending on the project. And it's important to note, by cutting away that volume geo, it really let us get a good simulation with a wide variety of inputs, as long as we got rid of those intersections. All right, so after the simulation, we move on to some post-cloth sim steps, and these were used for a couple different things. So first, since we simulated the cloth against that de-intersected volume geo, there was a chance that it could end up inside of the original skin geo. So for instance, this green geometry is the smaller skin geo, and this red one is the volume geo. So we take the volume geo, we carve it away, but it might leave sections where the skin geo is still popping through. And when we simulate the cloth on there, it's possible that the skin geo still sticks out of that cloth. So as one of our post-sim steps, we turn the skin geo into an SDF, and we push the cloth back out. And you can kind of see a more extreme example here, where you might see the body showing through, and we can push everything back out. Now, the post-cloth sim step is also a really important area where artists could make arbitrary adjustments to their sim, such as smoothing out any pops or jitters, or maybe the VFX supervisor wants a specific flap to open at a specific time. We can do some of that in the post-sim steps. And we realized as we went further and further along in projects, more and more of our fixes would be post-sim, because it was a lot faster, especially on a long shot, than resimulating everything. And it could end up being more art directable as well. After we finish with the cloth, we move on to taking that renderable cloth input and point-deforming it onto the simulated cloth. So essentially, we get the renderable cloth at the bind pose. We also get the simulated conform cloth of the bind pose. And in order to point-deform, we essentially have some special UVs that will be exactly the same between the thick cloth and the thin cloth. And that lets us transfer the animation over. And we also use their normals and the connectivity of different panels to figure that out as well. Once we have that data, that gets ingested into Weave, the animal logic tool set for making clothing. And it makes all of our work look very, very pretty. So that's essentially what we do with the cloth. Now from there, we have to move on to the fur. So the first thing we do is we need the cloth in a format to collide with the fur. We'd use VDBs for that. So we take the cloth, we turn it into a VDB, and here you can see the VDB itself, or well, SDF as we use it, but the sign distance field and the original skin geo that the fur is going to grow from. That's animated, of course. And basically the way we made this is we scatter a whole bunch of points onto the surface of the geometry, and we do a VDB from particles. And that lets us get a pretty accurate estimation of what that geometry is, regardless of how many holes it has or how bad the collision may have ended up. Basically, we don't have to do polycaps or anything like that. We just get a good SDF. All right, now for the hair itself, we start by bringing in a very dense geometry of curves. So in a production asset, this would be something like about 5 to 10 million curves per character. So obviously way too many to actually simulate efficiently. So we take all these hairs and we call them down. So they're probably about 10% of the original curves. Now, when we cut these down, we make sure that our new guides are based on the longest hairs in the incoming groom cache. And that's because when we simulate, those long hairs will stay under the surface. And so when we eventually interpolate back to the full hairs, we're more guaranteed that most of that full cache will stay under the surface of the cloth as well. And you can see sort of how much we cut that down in an actual asset. Okay, so once we have those guide hairs, we take them along with the USD animated skin geo, the skin mesh, and we do a bind of the hair to the body. Now this starts with just a kind of basic point deform, but our method has some pseudo collisions built in. And the way we do that is we take that guide cache after it's been basically point deformed, and we make a velocity field out of that from the root to the tips. We take that velocity field and we smooth it a bit. We also make a velocity field from the normal of the body, and this is going to help the hair from intersecting the body. And we add these two velocity fields together. We take that resultant field and we re-advect our hair through it from the root points. So it's going to more or less go where the hair started, but because of the nature of velocity fields, it's going to try to de-intersect itself, or just won't get intersected, I should say. And then the final step is we cut that back down to the original hair size. And you can kind of see a little bit of the difference of what this does, especially in joints and areas. It works pretty well, and it's fairly robust no matter what the input geometry is. All right, now after that, we take the bound hair and we do a basic fur simulation on it. So what does this all look like? Well, so here's an example of our guide groom bound at the bind pose, right? So it's just the 10% of the full groom. And if we just put our geometry of the cloth on there, the fur is going to obviously be sticking through that. So on the first frame of our simulation, we flatten the fur to the body. And then after it's flattened, we use that bound hair we did and use it as a goal so that the hair relaxes back to it. Also making sure that it intersects, or sorry, that it collides with that SDF. And that guarantees that our fur is always starting underneath the cloth. And so on a later frame, for instance, the bound hair might look like this, but our simulated hair looks like that. And you can see that in motion here. Now, 95% of the time on all characters and shots, this is all we really need to do for the fur. It was really basic and a very fast solution that was just built in a Houdini geometry solver. We did have a slightly more advanced method, and this higher quality method uses vellum. That had hair-to-hair collisions, hair inertia, it handled wind. You could plug in any sort of velocity field you wanted, get a little puffs of hair coming up. Now, this was actually originally done on a custom solver in Peter Rabbit, but we're transitioning over to vellum for current and future projects. We found that the speed got a lot better. Vellum let us make artist-friendly tools a lot quicker, and really it helped that newer people coming in would have a much easier learning curve. There's a lot of learning material for Vellum out there than if they had to come in and learn the entire custom solver for the advanced section. Anyway, after we do that basic or advanced first sim, depending on what the shot calls for, we export all that data, or sorry, we need to reinterpolate back to the full render cache. So our general method for this is we take that full groom and we also take our guide hairs. Now we look at the guide hairs to start and we see where their root points touch the surface. Then we look at any specific patch on the full groom and we see which root points of the guides are closest to it. Then whatever root points those were, those guides are the ones that deform that section of the full groom. And that's how we essentially interpolate back. This is that in motion. We found it works really, really well, relatively quick and accurate for short-haired characters. And even with the 5 to 10 million hairs, it only takes roughly 30 seconds to a minute per frame. And of course, it's not a solver, so that we can chunk up. After all that, we export the USD for the cloth and for the hair, and that goes on to trigger a render. All right, so how is it that we do all this within Houdini? So I want to give you a rough overview. I'm not going to go into every single node, but just roughly. To start off, we have a master template for each character. And this template holds a lot of different Houdini digital assets. So within the template, we have a section for specific large HDAs or digital assets that are going to be used in every single character. And the main parts of this are a template char effects rig HDA and a ROP network that helps us cache and export all the data. And it's really important to remember that those digital assets are the same on every single character. So when we do any updates of that are automatically folded into every single character on the floor. Now we also have sections for character-specific setups or shot-specific setups. We have a section for skin deformers. We have one for cloth simulation, one for fur, and any shot optional setups like wiggle or jiggling geometry or wind. So the main focus of this is this template HDA. And this holds all the connections between different sections of the rig, as well as data flow from input to output. So I'm not going to delve into all the details here because it's essentially just moving data around, but roughly we bring in USD data at the top. That gets split into different streams like the body or the cloth, the fur, whiskers. Everything is getting processed, moved around, the user can make changes. And then at the end, that all gets combined back again, and we write it out as USD overs and defines. So a really important aspect of this setup, and it's one of the big things we learned going from Peter Rabbit onto some current and future projects, is that we had these locked digital assets so we can update all the characters at the same time. But we also needed the ability for artists to make shot-specific changes. And we didn't want them going in and unlocking these digital assets because once they're unlocked, we couldn't update them. So while the template rig is locked, it works concurrently with shot-specific sections. So for instance, when we process volume geo de-intersection, inside the HDA, or inside our template rig, there is a volume geo stream. And we have a wrapped up HDA to help transfer data back and forth. Now, outside the rig, we have an equivalent section where the user is able to make changes. And I want to jump inside both of these nodes. So on the left, we have the HDA. On the right is the user section. So the first thing that happens is the HDA brings in a stream of data with the body geometry. Then the user section object merges that in. The user paints a color map and it sets some de-intersection properties. And then that data is object merged back into that HDA, which is then exported from this and goes back into the template rig. So the result of that is it added a little abstraction from the user side, but it meant that the HDA could be updated a lot easier. And because it's used for every single character, we can push out changes very quickly. We can also make some error checks here just to make sure that all the data is in the right format before it moves on to the next section. All right, that was that template HDA. We also have a ROP network. The ROP network we have is fairly sophisticated, and it really lets us take advantage of our render farm and split all these caches between different computers as much as possible. So throughout this, we have a ton of caches for every part of the process. We also have a lot of switches and logic, and this lets us be sure that this setup can handle many different characters. So for instance, if a character has cloth or if it doesn't, if it has fur, if it doesn't, if there's wind, are there collisions? Are we using the basic or advanced fur sim? We want this one setup to cover as much as possible. So to distribute these across the farm, we basically take any of the stages throughout the entire process that take more than a few minutes to complete. And I should say we're definitely taking advantage that we have a large render farm. Any non-simulated areas are chunked up even more to more efficiently put that out on the farm. And I should say it's really just a high-level view of the tasks here. The real thing is about 15 to 22 different caching nodes, depending on the setup for that character and for that shot. And we found that for about 100 frames of animation, this would maybe take 2 or 3 hours to complete, but it was all happening automatically in the background. Now, although there's differences between rigs for our characters, we did try to standardize them a bit to have some common parameters, such as, what kind of wind is being used, is collisions happening, what type of hair simulation. And many of those controls would be set up from our production database, which means some changes to shots, we never even needed to open Houdini at all. We could set that, the switches in the ROP would do their thing, and then that would work. Well, so that basically covers the automated pipeline, but how well does it actually work? Well, let's start with the good bits. So we got dynamic results for the animation department and for the director within a few hours of animation checking in their keyframes. On Peter Rabbit, at least, about 80% of the character/shots were automated without needing any CharFX department input. If shot work was needed, then it was easy enough for an artist to open something up, make a change, and feed that back into the pipeline. And again, any shot changes we fed back pretty easily. Also, it let the character test artists really focus on the hero work or the necessary parts of the sims. And the process was so successful, we even managed to get crowd shots working with it. And some of these would have up to 70 characters or something like that. Even in a shot like this, if we had to do specific work on 1 or 2 characters, it still meant 95% of it would go through automated. As our process matured, we saw hundreds of cloth and fur shots being automated that would get finaled straight from animation, including some fairly complex shots like this. All right, so the bad bits. Not everything always goes smoothly. So early rigs especially were very prone to failure, although that vastly improved as we went through our production. Part of the problem was that the rigs were quite complex and they really took a lot of time to learn. There's a few scenes we've had where characters are interacting with live action actors and actresses, whether they're getting pet or having their jackets, touched or something. We really struggled to make that work automated. There was just way too much specific setup per shot, depending exactly how the character was or the live action actor was filmed. We did have some automated collisions, but it really only worked on basic setups, like if there's a desk and a character's leaning on it, we'd get those, we'd figure out where those collision objects based on looking at proximity around the character and kind of work, but it only worked in basic scenarios. Sites like this were not uncommon until we had some quality control steps, but we'd figured out how to automate our blooper reel, so that was kind of cool. All right, so having said all that, we'd of course still get problems in the rig, either from unexpected input or bugs in the setup. So we started trying to find ways to fail smarter. So if we had a whole bunch of processes happening and one of them failed, we'd make sure that that stopped that chain from calculating, but let other projects in side branches continue. We also want to make sure we fail with very specific errors so that artists could find the problem as quick as possible. And it was especially important because in some of these shots and logs, they'd be checked by people other from our department, maybe a technical assistant in the animation department who wasn't that familiar with Houdini. So we wanted to be able to point out exactly where problems occurred. We'd also point out inside our digital asset where those errors were, and you can see how many error checks we had within that. And all of that tried to guarantee that processes that were already complete were still valid. So if we had to send something to the farm again, we could just pick up where we left off. All right, so our biggest issue that we want to improve especially is trying to find a balance between rigs that were easy to update and rigs that were easy to understand for the artist. So on Peter Rabbit, we did not have these massive digital assets. And it meant it was extremely difficult to update characters. So whenever we found a bug, which, depending where we were in the process or the show, could be once every week or two, or maybe multiple times a week, it would take 1 to 2 days re-implementing that fix into every single character we had. With the implementation of our massive digital asset, we fixed all that. It made it very easy to update, but it left a node graph that wasn't as easily followed for the artist. And also, if they needed to do something in the digital asset, that became unlocked and we can no longer update it. So part of our work in the future is to try to find an even better balance between some of those conflicting ideas. That's more or less what we've done so far. A little bit about some recent and future improvements we're looking at. Well, first, as I said, we've updated our first simulation to Vellum. We get a lot better results a lot quicker. And it's a lot more artist friendly to interact with. We've added some basic jiggle using chops to help in kind of fake muscles. And we've added a lot more error check nodes to really, if anything goes wrong, we want to know about it right away. We want to stop the processing of everything else on the farm. Now, what's our process to make sure that we're actually improving things? Well, basically, we treat our character rig as a program. And what I mean by that is that we are constantly improving it to handle more and more edge cases as we get them from shots. We fix any bugs as we find them. We make sure to get feedback from the artists. So if any artists have found common issues or they found solutions for problems, we make sure to put those back into the rig and update them for all characters. And finally, we create presets. For instance, if we're doing wind shots and we find things that are looking good, we want to make presets so that people can apply those right away. And we'll bake those presets into some of the digital assets so that they're available on all characters immediately. Of course, it's not really all automated. A lot of it is. But ultimately, we are not going for a realistic simulation. We want something that looks best on screen for the VFX supervisor or the director. So character effects artists are vital. Hero shots and others need art directable tweaking, and that could include for character interaction, collisions, wind setups, pops, jitters, or any general misbehavior of the sim. So while the artists are always very important, the automation process we have improves that efficiency throughout the pipeline. And even with all the automation within character effects, without the rest of the Animal Logics pipeline, we basically wouldn't get an excellent looking render. So this includes any update to assets automatically delivering to downstream departments. We have an automatic first pass of lighting based on some LiDAR and plate projection. We have Alfro, which is our tool set for grooming and rendering hair. We have Weave, the tool set that makes all the cloth look nice. And we have Glimpse, our renderer that makes everything look really pretty in the end. So that's essentially it. Most of our shots go through automatically. The real benefit is that we get these rich dynamic renders within hours of animation checking in something. And that really helps feedback and gets iteration much, much quicker. Of course, the automated rigs don't build themselves. So I really like to thank the ChartFX team leaders and the CG supervisors, the effects TDs for building the Anim CFX process, the performance TDs for managing it all, the R&D team for the Alfro and Weave and Glimpse brilliance, and of course the animation team for really putting up with us and putting their faith in us, because it really was a good team effort. If you're interested in becoming part of the team, please go ahead and check the website for positions that we're currently looking for. And also, there's a few other talks from Analogic people today. So the owner, Zara Albanian, will be talking at 11:15 about empowering storytellers through technology. And Aidan Sarsfield is talking at 4:15 about efficient pipeline management. Also, if you're interested in how exactly we used USD, come back here at 1 p.m. Luke Ravitt is going to be talking about forging a new animation pipeline with USD, and he'll go into a lot of the details about that. And that essentially brings me to the end of the talk. I hope it was helpful, and if you have any questions.
Thanks, Adam.
Thank you.
Any questions?
Make it easier for me.
I want to throw this thing. Come on.
Just a quick question about the postfix you're speaking about.
About the what?
The postfixing.
Yeah.
Do you do it every substep, or you do it for after the simulation is done?
No, we don't really need to bother with substeps for the post simulation, because the cloth simulation has been the thing that takes care of any quick motions and making sure that everything interpolates correctly between frames. Usually the post setup is just to smooth out jitters or to add specific things that they might want after that. Like maybe something stayed stuck underneath the body somewhere for some reason, so we could bring it back out, delta mush it, smooth it, make it look like it was good. There might even be sections where the sim looks great everywhere, but around the elbow, it's just kind of doing something. We might freeze it at a frame and point deform it to the elbow just for that section, and then blend back to the sim later.
That's it. Okay. Yeah. Thank you.
Yeah.
Something back here.
Was using Marvelous Designer, was that just a design choice, or?
Yeah, I mean, I can't speak too specifically why it was done in Marvelous. That was a little outside our realm, but I believe it was a design choice. They were getting good results from what Marvelous was giving us. It also did have the advantage that it gave us those flat panels also. And those flat panels were very helpful in the cloth simulations themselves, relaxing back to the state that they should be.
Cool.
Hey, those velocity maps that you created,
Yeah.
were they just linear by distance, or was there an algorithm to create, or were they created by hand?
You mean for our binding step when we do our pseudo collisions?
Yep.
No, we basically would take each hair, go from root to the tip, and just make the velocity go along that curve. And then by smoothing that and by adding in that normal from the body, that resultant field, almost by definition, is not going to be intersecting, because the VDBs are going to be, or the velocity fields will be separating. And then when we read it back through, we're pretty sure that our hair won't be intersecting anything. When there's real extreme poses, there's still going to be some intersection, and that's when we'd have to do some of the advanced vellum stuff to make sure nothing's intersecting that body.
All right, that makes sense.
Any other questions? Going once, going twice. Okay, thanks a lot, Adam. Oh, one more.
You didn't speak about interaction between two characters.
Yeah.
Use it hug each other. How do you handle this?
Yeah, so, okay, interaction between characters. We've had a couple tries at automating that. The basic idea was we bring in our main character. We have all the other characters as well from USD. We do a kind of every 10 or 20 frames check to see if any of that character is intersecting another character. If they are, then we do the equivalent of our volume geo de-intersecting fix, but we basically de-intersect it from the other character at something like half the amount we normally would. And then the other character is also de-intersected about half the amount. And that tries to leave space in between them to let both of their clothing sit. Practically though, while that worked on, we'd have a couple shots and we'd be trying it and it sort of worked. Once we got to actual real production shots, there's just a lot of notes and feedback. And because it's two hero characters, they're really getting scrutinized a lot. And so the automated process kind of worked, but more or less might give us something to start with, but we still need to do a lot of manual work for that. But at least when that manual work was done, the rest of the system runs automatically after that. So we can pass those cloth changes or those geometry changes back out, and then they go on. Thank you. Hey, you threw it finally.
Did the setup work well with multiple layers of cloth?
Yeah. Now, yeah, it really did. I didn't quite go into some of the details of this, but in that user setup section, that has a cloth simulation section that's different for every single character. It has the same inputs and outputs, so it's object merging the cloth inputs from the template rig and exporting them back there, but the setup itself would be done per character, because that was one of the things that obviously, depending exactly how that character setup is going to be different. Yeah. So there were, yeah, I really didn't show exactly this, but there is still a lot of manual setup per character. It's just that we have this system to hold that all together and to automate all those parts.
Anything else? Okay. Thanks, Adam.
Yeah, of course.